The purpose of this video is to explain how to derive the results shown. Please note a quick buyer beware. The approach here is unorthodox and has undergone no external vetting. Most viewers have probably heard of the Planck length. The value is obtained as a means to find units that are universal. Another way to think about this is that the units reference fundamental properties of the universe and thus do not depend on an arbitrary scale. Interestingly, approximately 30 years before Planck introduced his units, another physicist named George Stoney introduced a similar construct. The motivation for his units were similar, however, the key difference was his focus on connecting the force of gravity to the electromagnetic force rather than a focus on the Planck constant. Remarkably, the two lengths are related and only differ by a factor of the fine structure constant. There will be much more to say about the fine structure constant later, but for now, note that it represents a dimensionless value, so does not affect unit analysis in any way. However, it plays a critical role throughout quantum field theory, so one might not be surprised that it plays an important role here. Thus, while the Planck units have dominated the discussion for the last 100+ years, the view adopted here is that it is the Stoney length, or Stoney units, which are more relevant and interesting to consider. Along with the Stoney and Planck lengths, the idea presented here is to propose a third length called the fundamental length. The fundamental length here, indicated by L subscript f, is hypothesized to represent the smallest distance at which an extrinsic electromagnetic effect can be distinguished. Our goal moving forward is going to be to derive this length from first principles, and in the process demonstrate that it is equivalent to the Stoney length, as well as elaborate on what this fundamental distance actually represents. We began this pursuit by first looking at the permittivity of free space, epsilon naught. There are different ways to represent the units of epsilon naught, but for our purposes, the most useful representation is given by Coulomb squared divided by joules times meter. Now, although the vacuum permittivity is considered a fundamental constant, it is written in units of arbitrary scale. Put another way, the meter, the joule, and the coulomb represent units that are useful at a human level, but are not connected to the scale relevant to fundamental particles. As a result, a better way to represent epsilon naught is to map each of its units to a fundamental scale. Notice that in each of the three terms, we are not changing the unit. Charge remains charge, energy remains energy, and length is still length. The difference is we are simply scaling the arbitrary value of a coulomb of charge squared to the fundamental level of the elementary charge squared. In a similar manner, we scale the arbitrary amount of a joule to the rest energy of the electron. Finally, the meter is scaled to a fundamental length, which at present we don't know what it is, so is simply hypothesized to exist. Our goal will be to determine this value. Putting this all together, we can reproduce the permittivity of free space, but at the fundamental scale associated with the elementary charge, rest energy of the electron, and the hypothesized fundamental length. It's anticipated that the form of epsilon naught shown here will be unfamiliar to most, so it's worth looking at this closely. The constant still represents a value of charge squared divided by energy times length. However, instead of being provided at the scale of the arbitrary units, the coulomb, joule, and meter, it has been translated to the scale of the electron. There are a couple crucial points to note here. First, notice that the value of epsilon naught remains on the right side with the scaled units. In other words, the typical value associated with the vacuum permittivity, i.e. 8.854 times 10 to the minus 12, remains attached to the scaled elements. In effect, this appears to invert the units, but the situation is more nuanced. What is really happening is analogous to Planck's motivation, but rather than trying to map the fundamental constants h, c, and g to the number 1, the goal here is to go one step further and find fundamental values such that the permittivity of free space itself is equal to 1. Using this as the base, it's trivial to rearrange terms to bring the unknown length scale to one side, leaving all known constants on the other. However, the second crucial thing to note is that this expression represents the diameter, or rather the full length separation between two particles, each with its own radius, such that their combined distance is equivalent to a diameter. Our interest is in the length associated with only a single representative particle. Thus, we need to divide the result by 2 to obtain the hypothesized radius. Perhaps another way to think about this, which may be more intuitive, is to consider the nature of epsilon naught. The numerator represents a value of charge squared, which implicitly describes two particles, when our actual goal is to define the fundamental length with respect to a single particle. As such, the value obtained by the evaluation at the fundamental scale effectively double counts the length associated, as it references the distance between two particles. We only need one particle to define a fundamental length, so the solution is to divide by 2 to avoid this double counting. Already, inspection of these two values shows that the fundamental length just obtained is quite close to the stony length derived over 150 years ago. Moreover, if one simply stopped here and used the fundamental length derived so far, one would obtain a derived value for the gravitational constant g that is only about 1% different from the empirical value. What follows is a modest correction, which provides deep insight into the nature of the fine structure constant alpha, as well as the fabric of spacetime itself. The following idea is a bit abstract, so we will approach it stepwise. The key idea here to consider is the concept of distinguishability. In the next few slides, we will investigate this concept. There are two circles on this screen. I'll pause for a moment to see if you can find them. Okay, it may be hard to see them both, so let's trace each one in a different color. The first one is red. It has a center drawn by the point and an arrow which represents the radius. And I'm going to guess that you found this one. So you probably found circle 2, but just didn't realize it. It has the same center and the same radius. Here it's drawn in blue. In other words, circle 1 and circle 2 are indistinguishable from one another. Now, consider what it would take to distinguish circle 1 from circle 2. A naive guess might be to suggest a separation between their two centers, here labeled as delta, such that any delta greater than 0 will do. Here, we've inserted a Cartesian coordinate system such that the y and z axes are orthogonal to the motion of separation, and the x-axis is parallel. It is true that any observer situated in the YZ plane should, in theory, be able to identify any separation between the two circles. But let's consider the perspective of an observer situated on the x-axis. The crucial point to consider is that only when all observers agree that the objects are fully distinguishable can we indeed say they are distinguishable. Put simply, we are limited to our weakest link. It's difficult to rotate this coordinate system to be aligned with the x-axis, as we are limited to 2 dimensions, so this image is still given as a cross-section, but we can use our imagination to complete the picture. There is no motion along either the y or the z axes. As a result, the width will not change and the height will not change. The circle will remain a circle. Moreover, if we accept the central tenet of relativity, namely that the speed of light is finite, then the observer along the x-axis is forbidden from being able to see that the two objects have separated until the separation has grown to at least twice the radius. To put this another way, imagine the two circles have separated by a distance delta, which is less than or equal to the diameter of one of the original circles. Now, our x-observer has decided that the two circles have indeed separated and are distinguishable from one another. However, we need to verify this fact. The only means this observer has to do this is to hop in a spaceship and travel the full extent from the leading edge to the trailing edge of the circle, which is equal to the diameter. However, relativity tells us the observer can't travel faster than the speed of light. If by chance the circles are separated by any amount less than the diameter, then it's possible that the two circles could move back together, also at light speed, such that by the time the observer moving along the x-axis reaches the trailing edge, the circles have recombined. As a result, there is no way for an observer constrained to move along the x-axis to have advanced knowledge until the circles have separated by twice their radii. Or is there? Now, let's play a little game. Our observers situated along the YZ plane are a little flustered. They complain, why do we have to wait until the two circles are completely separated in order for all of us to agree that they are indeed distinguishable? Isn't there something we can do to speed this up? So they put their heads together and get clever. They notice that generally speaking, there are two ways for the circle to move along the x-axis such that the motion is indistinguishable for our observer on the x-axis. In the top version, the circle simply translates to the right. In the bottom version, the circle rotates such that if we imagine there were tiny labels attached to the circle, then as it moved left to right, it also rotates such that these labels move counterclockwise about the circle. The key thing to realize is whether the circle translates without rotation or translates with rotation, an observer along the x-axis is none the wiser. Now, it might not be apparent why allowing the circle to rotate as it moves helps the conspirators along the y and z axes. But remember, they are clever, so they are planning to play a little trick on our x-axis observer. To see how this trick works, we are going to focus on one circle and label 2 points, L and T. Notice that point L over here on the left is aligned with the x-axis in our initial position, and point T is located at some arbitrary point along the circle, but crucially not on the x-axis. Now, importantly, if we look closely at the initial and final endpoints, we will notice something interesting. Recognizing L represents the leading edge, or rather the point that our observer along the x-axis first encounters on the circle, we notice that at the final time point, the leading edge is no longer aligned along the x-axis. Instead, it is at some arbitrary point along the circle. Similarly, the point we labeled capital T, and we will now associate as the trailing edge, is not on the x-axis at the initial time point, but it is at the final time point. To put this another way, if we define a new variable d prime, which represents the distance between the leading edge at the final position versus the trailing edge at the initial position, our y and z axes can trick the x-axis observer into thinking that this distance represents the full diameter of the circle. The reason for this is both L and T are on the x-axis when the x-axis observer passes those respective points. And this is all due to the fact that the x-axis observer cannot distinguish between simple translation of the circle versus translation with simultaneous rotation. The question now becomes, how do we determine this faux diameter that the y and z axes trick the x-axis observer into seeing? To do this, let's consider the angle theta, which represents the angle describing the arc between the last 2 points of contact between the overlapping circles, here labeled as A and B. The point P represents the center of the red circle, so that the distance PA and PB are the same and simply equal to the radius. We can draw a new line from the point A such that it intersects the line segment PB at a right angle. This triangle is recreated below, and a simple trigonometric relationship allows us to identify the distance L as r cosine theta. Now, We're going to add two more points labeled C and C prime. These represent the halfway points between A and B along their respective circles. So point C is the halfway point between A and B on the red circle, and point C prime is the mirror image just on the blue circle. If both circles rotate counterclockwise at the same rate, then the red circle will travel along the arc BC, while the blue circle travels along the arc A to C prime, because both of these arcs are represented by the same angle, namely theta over 2. However, notice that the length L lies along the radial path from P to B. Similarly, L prime lies along the radial path P prime to A. As a result, after both circles have rotated by an angle theta over 2, then L and L prime will lie along the direction of separation of the two circles, or rather the x-axis in our description before. Crucially, the length L, which equals L prime, represents the distance light would have to travel along the axis of separation, such that the circles rotate the arc lengths AC prime and BC. So now we can put this all together, and we can identify the length L as the unique length of the new radius that describes the event where the circles remain in contact but are separated completely, and thus fully distinguishable from one another. If we were to consider any other angle, here labeled as delta, then after an equal amount of rotation by both circles, the result is either still a state of partial overlap, or we've gone too far and there is a separation between them. The reason for this is our x-axis observer is a very keen observer. Any rotation different from theta will result in the points L and T from our earlier picture no longer being aligned with the x-axis when that observer is passing those points. As a result, in these circumstances, our x-axis observer will be alerted to the trick that the y and z axes are playing. Only when the rotation is equal to theta does a unique state exist where the x-axis observer can be none the wiser. Now, at this point, we might be wondering what the angle theta is. In a moment, we will see that the fine structure constant plays a pivotal role here. But before we do, we need to extend the concept presented here to 3 dimensions. Okay, so far we've been discussing the idea of distinguishability for 2-dimensional objects. The reason for this is straightforward. It's hard to represent 3-dimensional objects on a 2-dimensional surface. Moreover, it turns out that while there are some nuances that need consideration when extending the ideas from 2 dimensions to 3 dimensions, most of the intuition can be developed within the simpler model. As a result, there are only a few modest changes we need to make. First, in moving from 2 circles that overlap to 2 spheres that overlap, we change from thinking about planar angles to solid angles, here labeled as omega. If solid angles are unfamiliar, there are a number of excellent resources online, and a simple search should turn them up. A second major difference from 2D to 3D is that while a circle can rotate along one axis, a sphere can twist along a helical path. This motion, commonly referred to as screw motion, is well developed in the study of rigid bodies. It is suggested that it represents the fundamental description of motion. As we extend into 3 dimensions, we first look at a radius from one sphere to the last point of intersection with the other sphere. In general, as we consider helical or twist motion, this radius will have an x, y, and z component relative to our axis of separation, such that we first need to project it onto a plane. This is done by the simple r prime equals r cosine theta. From here, the analysis can proceed identical to the process described for the 2D case. The end result is an extra cosine term of half the solid angle. Okay, it's helpful to do a quick recap. We started out with the permittivity of free space, epsilon naught. We sought fundamental units that would map this constant to the number 1. This gave us a fundamental distance, which we labeled L. However, this distance represented the diameter of a hypothetical fundamental distance, so we mapped this to a radius simply divided by 2. This gave us a fundamental length. Along a similar line of reasoning, we also identified this fundamental length with a concept of distinguishability between two particles. Our first attempt was that any separation would do. This view is similar to the Newtonian perspective of instant universal propagation of information. Our second guess was motivated from special relativity and resulted in an estimate of twice the radius. However, this view is equivalent to treating spacetime as flat, which is at odds with ideas from general relativity. Thus, we produced a third result. This more nuanced view exploits the idea that spacetime is not static, but the solution it produces creates a new problem. We are left with a solid angle omega that seems like it could take on any value, such that instead of creating a well-defined value for the fundamental length, we are left with a continuous set of values. The solution to this problem will reveal a great deal about the fine structure constant alpha. But first, let's think about the problem geometrically. The surface area of a sphere is just 4 pi times the radius squared. If we think about the solid angle, we can see that in separating the two spheres, it progresses from 0 to 4 pi. Thus, we can think of omega over 4 pi as representing a ratio that ranges from 0 to 1. As a suggestive hint, both omega and 4 pi are solid angles, so their ratio represents a dimensionless quantity. More to the point though, the fine structure constant is defined as a dimensionless constant that quantifies the strength of the electromagnetic interaction between elementary charged particles. Recall what our chief objective in this exercise is. We are seeking a fundamental length, or separation, which distinguishes between two particles. Below this fundamental length, and our two particles become electromagnetically indistinguishable. Crucially, the fine structure constant is defined as the coupling constant which defines this strength of interaction. In order to have an interaction in the first place, two objects must exist, so the fine structure constant is intimately connected to the fundamental length, or fundamental measure of distinguishability. Now, it turns out that the ratio of omega over the solid angle of the unit sphere 4 pi set equal to alpha introduces a small error. Essentially, if we think back to the trick that our observers seated along the y and z axes play on the observer placed along the x-axis, recall that they attempt to shorten the perceived diameter of the x observer by allowing the particle to rotate as it moves. Eventually, we related that shortening to the solid angle omega. However, this process, or trick, that the Y and Z gang employed effectively treated spacetime as if it was a rigid structure. Comically, their fix was to bend spacetime by first treating it as a static object. Perhaps another way to think about this is that effectively we realized spacetime wasn't fixed, but in order to correct for this non-rigidity to spacetime structure, we first fixed spacetime and then calculated the correction. Put more simply, we have to correct the correction. Fortunately, all the preceding logic applies. The only difference is the scale at which it operates. So we collect a second term, alpha squared. Of course, this sets up an infinite recursive process. We need to correct the correction to the correction. Hopefully I said that right, but in any case, I think you get the idea. Although the infinite power series may look messy, it turns out to have a very clean solution. A simple rearrangement of terms gives us omega. Recall from earlier, we found a rigid fundamental length from the permittivity of free space. Also, it's important to remember that the manner in which the vacuum permittivity was manipulated. It carries the value, but the units are flipped from the form most are probably used to viewing it as containing. Although this may seem peculiar, recall also that this representation is no different than simply seeking a fundamental unit scale such that the permittivity itself is equal to 1. Now, if we put the ideas together, we can combine the rigid length with the concept of distinguishability to produce a final fundamental length as shown. Essentially, the fundamental length is just the value obtained from the vacuum permittivity, but adjusted by the two cosine factors to account for the constancy of light propagation and its effect on distinguishability for an electromagnetic event. Consider the fundamental length we derived with respect to the stony length derived over 150 years ago. At this point, we can invert the process that George Stoney employed. In his efforts to examine the nature of fundamental units, Stoney examined the situation where the gravitational force was equal to the electric force. In his case, he treated the constant g as a known along with the other constants. Namely, m1 and m2 are the electron rest mass in kilograms, q1 and q2 the elementary charge, 4 pi epsilon naught the electric permittivity. Note, here it'd be represented in its more common form, and the term Re, the classical electron radius. For those of you who are unfamiliar with the classical electron radius, it is simply the value one obtains from considering the energy required to assemble an amount of charge onto the surface of a sphere such that the energy is equal to the rest energy of the electron. Synthesizing, we can write an expression for the gravitational constant g from all known constants. Now, due to the various connections between epsilon naught, mu naught, and c, it's possible to express g in different equivalent forms. The form shown here happens to be the preferred version, as it keeps separate the two factors of epsilon naught which carry the value but come with reciprocal units, as already discussed. Other forms tend to mix these, and thus it adds additional care in keeping track of the units, but they are equivalent. In any case, evaluation of the derived expression results in strong agreement with the empirical value, particularly when it's noted that there is a fair bit of uncertainty surrounding the empirical value. Measuring g is extraordinarily difficult, and the uncertainty bounds surrounding the most precise measurements of g are outside the standard deviation from one another. As a result, it is claimed that the value derived here is in strong agreement with the experimental value. At this point, we've derived the gravitational constant g, but there might be some additional questions. And so it's worthwhile to explore some of the properties of gravity, which includes concepts from general relativity and how these concepts connect with the ideas presented so far here. We have been discussing everything from an electromagnetic context. As a result, two things which may jump out are the fact that gravity affects all particles, including electrically neutral particles, along with the fact that gravity is universally attractive. These ideas may seem at odds with the well-known properties of the electromagnetic force, which appears to only affect charged particles and can be both attractive and repulsive depending on which charges are present. In a moment, we will break open those ideas to see how they tie in to the electromagnetic perspective of the gravitational effect. But first, we will consider some simpler ideas. The approach taken in this derivation gives us the first three of these properties for free. We are implicitly assuming in relating gravity to an electromagnetic fundamental length of distinguishability that ultimately gravity is nothing more than a manifestation of the same underlying phenomenon which defines electromagnetism. To put this another way, the onus isn't on trying to figure out why gravity just happens to be identical to electromagnetism such that it follows an inverse square law or propagates at light speed. From the view adopted here, it would be more challenging and alarming to try to explain why they are different. In essence, if we were to say that they were different, then it's as if gravity and electromagnetism are based on the same underlying physical phenomenon, but obey different principles. In other words, the electromagnetic field propagates at some speed, but the same electromagnetic field propagates at a different speed when it becomes self-referential. It's simply illogical to suggest that two things which are ultimately due to the same underlying phenomenon obey different laws. Thus, the idea of propagation of gravity at light speed comes inherent to the fact that it is ultimately an electromagnetic phenomenon. Similarly, the notion of inertial mass versus gravitational mass is irrelevant. Mass is an electromagnetic property, period. Now, as mentioned, the idea of how an electromagnetic phenomenon interacts with electrically neutral particles, or the notion that it must always be universally attractive, may not be obvious, though ultimately the reasoning here aligns with the concepts of general relativity quite nicely. However, the context here is different, so we will examine some of the subtleties and explore how all three properties stem from the same idea. However, even though they are connected to one another, it's best to kind of do them one at a time. The following represents a list of all neutral fundamental particles with the exception of the Higgs boson. Some of these may be easier to imagine as possessing a strong link to an electromagnetic associativity. For instance, positronium is just an electron mixed with a positron. If we're struggling to find charge there, we might have other problems. Others, like the photon or neutrinos, may not be so straightforward. However, see if you can notice anything about all these particles. Every one of these fundamental particles outright, or in the case of the neutral mesons and hadrons, which are composed of the more fundamental quarks, possesses a non-zero quantum value of spin. Collectively, these particles can exist in a state where the composite system has a net spin of zero, but crucially, at the individual level, these all possess some value of spin. Moreover, spin represents an intrinsic form of orbital angular momentum. Now consider what we have done in describing gravity. The principal motivation was to define an electromagnetic intrinsic distance, a so-called fundamental length of distinguishability. In other words, intrinsic angular momentum aligns with this notion of intrinsic distinguishability. The key word here being intrinsic. The key takeaway here is there are two types of electromagnetic interaction: extrinsic and intrinsic. Extrinsic interaction is the type we are most familiar with. This is an electron interacting with a proton or an electron being repelled by another electron. This type of interaction is extrinsic because external observers are affected. An intrinsic interaction, by definition, does not directly affect an extrinsic observer. In a sense, one can think of the intrinsic interaction as the electromagnetic interaction that results from acceleration. Acceleration produces a change in energy state, which in turn implies a self-interaction with the particle's own electromagnetic field. So another way to think about this is that while a neutron, a neutrino, or a photon possess an extrinsic neutral charge, meaning they exert no extrinsic electromagnetic force on other particles, there is nothing to preclude them from possessing an intrinsic charge distribution. Perhaps to drive home the point, imagine a fictitious bag in which a bunch of electromagnetic charges are stuffed inside. Now the net charge for any observer outside the bag is zero, but inside the bag, the charge distribution can be shuffled about. The only requirement is that no matter what shuffling is done, all external observers must agree that the net charge on the surface of the bag is zero. Now this may sound impossible, and if we assume extrinsic electromagnetic interactive distance can take on any length measurement, then perhaps it is. But importantly, with the fundamental length defined here, we don't accept that the electromagnetic distance of distinguishability can go infinitesimally close to zero. Instead, this distance is finite, and this comes with important consequences. It suggests that, roughly speaking, as long as the particles hidden within our bag move at distances less than the fundamental length, then we as observers on the outside can be none the wiser. In other words, it seems like an apparent paradox. The charged particles in the bag are moving all about and claim that their distribution relative to one another is changing. But because this change is happening at a distance below any change that can be measured externally, all observers outside the bag claim nothing has happened. Importantly, however, while observers inside and outside disagree, there is nothing to prevent the charged species inside from interacting with one another relative to one another. The key takeaway, though, is Mother Nature never allows a free lunch. In order to reconcile the perspective of the particles inside the bag moving all about relative to one another, there exists an intrinsic electromagnetic interaction between them. Now, all this may seem far-fetched, with a hypothetical bag and charges inside that no one situated on the outside can observe. But consider what the standard model suggests a hadron like a neutron is. It's a collection of a lot of quarks, which are charged species that can never be measured individually. Quarks, by assumption, take no independent extrinsic form. Instead, they are understood to be an intrinsic part of the composition of each hadron. According to the view adopted here, gravity is an intrinsic manifestation of the electromagnetic force that arises from self-interaction. Thus, while the electromagnetic force in its more orthodox form governs extrinsic interactions between particles, the claim here is that gravity represents an intrinsic electromagnetic self-interaction. This view is supported by the fact that all of the neutral particles listed previously possess an intrinsic non-zero value of spin. In summary, photons represent oscillating electromagnetic fields. Hadrons are collections of charged quarks. Neutrinos and Z-bosons are fundamental particles which mediate the weak nuclear force, which in turn transforms quarks from one version into another. Although these particles possess no extrinsic electromagnetic effect, their intimate relationship with extrinsically charged particles, coupled with their own intrinsic properties, suggests there is no reason that each could not self-interact electromagnetically. It's well known that gravity is universally attractive, but the electromagnetic force is both attractive and repulsive. How can we reconcile the idea that gravity is nothing more than an intrinsic version of the electromagnetic force when it does not exhibit identical behavior? It's helpful to first consider the fundamental ideas associated with general relativity. In general relativity, gravity is no longer viewed as a Newtonian force pulling two objects together, but rather a warping of space-time by mass and energy, such that the more mass and energy there is localized in a region, the greater the warping of space-time. From this perspective, gravity is a geometric construct, wherein objects attempt to move along straight lines, but are restricted to follow the curvature of space. The view adopted here aligns with and supports the geometrical interpretation produced from general relativity. Namely, the very concept of electromagnetic distinguishability represents a contraction of spacetime. In the drawing, notice that space is contracted from the original blue circle to the new dashed green circle, and critically, recall that this contraction is spherical, or really four-dimensional, technically speaking. So while it may be difficult to imagine a sphere that contracts about its center and is surrounded by other spheres in a four-dimensional space-time, this represents a direct physical model for the bending of space-time. Here, the greater the distinguishability, or rather acceleration, the greater the warping of space-time, in concordance with the view from general relativity. Thus, the idea of universal attraction can follow the same reasoning as general relativity. The very fabric of space-time is warped due to acceleration. But importantly, as the fundamental length represents a defining minimal length, this approach opens the door to quantization and a path towards reconciling general relativity to quantum theory. Although the physical distortion of space-time just mentioned supports the same geometrical interpretation of gravity provided from general relativity, it's worth mentioning a related feature, which is that gravity is an intrinsic restorative effect. Put another way, if we consider the blue circle on the left, with the black arrow looping back to the shaded green circle, representing a self-interaction from where the particle previously was, it becomes obvious that regardless of the direction of motion, the self-interactive component always points back to the location of the original source. Thus, while an extrinsic force can push a particle along any axis in space, in sharp contrast, the nature of self-interaction always points back to the center, or rather its point of origination. In essence, this description is analogous to the tidal force associated with the variation in a gravitational field, which results in elongation or stretching of an object that is composed of multiple particles, and which demonstrates the relationship between the equivalence principle versus the curvature of spacetime. Moreover, this restorative component will always oppose itself, such that it will appear to the original charge as if a charge of opposing sign is acting upon it, so to speak. As this source of opposing charge always originates from the true object's inertial state, the object will be universally drawn back towards that space-time coordinate. The consequences of this restorative effect become more pronounced as we expand this picture to the surface of a sphere. In some sense, if space-time were perfectly uniform, then the restorative effect from gravity would cancel out everywhere. However, the moment there is any non-uniformity, this breaks the destructive interference such that the restorative effect towards the center of non-uniformity receives a constructive boost and vice versa elsewhere. This, of course, follows an inverse square law due to the surface area being proportional to the radius squared. Thus, in summary, one can think of the universal force of attraction that we associate with the force of gravity as a desire from nature to return towards a state of electromagnetic indistinguishability. All right, the next two slides are a speculative digression, but it's being tossed in because it's a fun idea. First, notice that gravity, as described here, is representative of a measure of the non-uniformity of intrinsic self-interaction present across spacetime. The identification of the presence of dark matter in the cosmos promotes the highly speculative suggestion that dark matter is in essence a measure of the intrinsic interaction between matter trapped within black holes. The consequence of this would be an acceleration of matter towards that source. As black holes are spread extrinsically throughout spacetime, this implies that matter is attracted simultaneously to disparate points. Consider the simple case of a 1D universe, such as an object located at a point on a line with two black holes placed at the ends of that line. If the object experiences a force of attraction towards both black holes, it can't move in either direction, as this will result in favoring one or the other. However, there remains a resolution in that the particle could contract the line such that both black holes appear to move towards it. In other words, the ends of the line move towards the center. Note that this would give the appearance of additional matter located somewhere along the length of the line. Mapping this to our 3D world, intrinsic interactions between black holes separated extrinsically relative to us would give rise to the appearance of what would seem like hidden matter. Thus, dark matter and its distribution throughout the cosmos under this description represents a measure of interaction between black holes. Finally, note further that the distribution of hidden matter produced from the intrinsic interaction need not be uniform. Here we've added a third black hole to produce a plane, and if we consider different amounts of intrinsic interaction between different black holes, then the appearance of hidden mass would reflect this variable exchange. All right, returning back to the main topic, while it may seem that neutral particles and universal attraction are at odds with the idea that gravity is nothing but a component of the electromagnetic force, the premise of the idea here is that gravity is nothing more than the intrinsic component. The intrinsic component is by definition a self-interactive component. It is not subject to the same constraints imposed on an extrinsic interaction. Instead, it represents a restorative effect that acts universally on all particles that possess any intrinsic spin angular momentum. To address the issue of the Higgs boson, which is extrinsically neutral and possesses no spin, there are a couple things to consider. First, the Higgs boson is an unstable particle. It decays into other particles which are subject to the above considerations. Since the Higgs cannot exist independently in some sense for all time, one could define it as a collection of the other particles existing in a unique relative state to one another. Under this view, the arguments that preceded immediately apply. Going a bit further, though, the Higgs boson, along with its corresponding field and mechanism, are unique as they are proposed to explain the generation of mass within the Standard Model. Along this vein, one can transfer the concept of mass onto the concept of intrinsic spin. In effect, saying the Higgs mechanism is ultimately responsible for producing the property of spin, which in turn is responsible for generating mass. We can now address the last main property which is why there exists an enormous difference in the strength of gravity versus the strength of the electromagnetic force, even though the same phenomena underlies both. Consider a toy universe consisting of just 10 particles, and further suppose that the arbitrary particle we label with the number 1 receives a push from another particle, let's just say particle 8. Now, particle 1 is absolutely certain that the push came from particle 8. But particle 8 says, whoa, how do you know it's my fault? In fact, particle 8 says, let me tell you what really happened. Particle 8 says if we travel way back to yesteryear, an arbitrary other event in spacetime that happens to be in the past relative to particle 8, we will see particle 1 bump into 3, which bumps into 6, which bumps into 10, which hits 5, which hits 8, such that the end result is 8 collides with 1. In other words, particle 1 claims it was all extrinsic. The shove came from an external source. At the same time, particle 8 says, no way. I may have hit particle 1, but the driving force began long ago and stemmed from none other than particle 1 itself. This represents what seems like an apparent paradox. Now, with respect to neutral particles, resolving this ambiguity is easy. Neutral particles experience no extrinsic electromagnetic forces, so neutral particles are 100% confident that any acceleration they experience must be the result of some self-interactive component. In other words, they experience gravity, but no electromagnetic force. Charged particles, on the other hand, are a different story. They are subject to both extrinsic and intrinsic forces, but they're unable to tell the difference between them because they both arise from the same underlying phenomenon. So, from the perspective of a charged particle, they are indistinguishable. But particle 1 realizes something. There are more external particles and only one of it. In other words, there are more ways to assign blame for the force to an external or extrinsic particle, but only one way, no matter how convoluted that force could have originated from particle 1 itself. As a result, we see that the enormous difference in magnitude between gravity and electromagnetism is fundamentally a measure of how big the universe is. In essence, if we imagine a single electron undergoing an acceleration of some sort, there are a lot of particles encapsulating electromagnetic energy extrinsic to the electron, such that with almost near certainty, the electron can be confident that the acceleration came from an extrinsic source. Almost entirely confident, but nature keeps track. Of course, the ultimate magnitude of the intrinsic versus extrinsic effect of the electromagnetic force is set by the values of the fundamental constants themselves. However, with this in mind, it brings up an interesting philosophical point. If one assumes these fundamental constants are indeed constant across all spacetime, then this, coupled with the quantization of spacetime, suggests there exists an upper bound for the extent of the universe. Note, this does not imply the upper bound needs to be finite. Rather, it is at most countably infinite. Obviously, the idea presented here has some profound implications. By far the most substantial idea to emerge is a philosophical definition for the nature of time. Defining a fundamental measure of distance through the constancy of the speed of light, we also get a fundamental definition or quantized unit of time. The geometrical description for the fine structure constant is elegant. It represents the ratio of the solid angle associated with the fundamental length, normalized to that same solid angle plus the unit sphere. In other words, it defines electromagnetic interaction through geometric distinguishability. Incredibly, however, there are at least two additional representations of the fine structure constant that produce additional insights which are aimed to be explored later. However, one final thought that seems fitting to wrap things up here is to chime in on the storied debate over the existence of an ether. Although only mentioned in passing, The view adopted here is ironically more consistent with the thinking of Fitzgerald and Lorentz circa the 1890s. It supports the idea of a physical representation of a fundamental particle like an electron, as well as an enhanced meaning to the curvature and true nature of spacetime. Thank you for your attention.